Every radio receiver performs one essential function. It extracts a low-frequency information signal, known as the baseband, from a high-frequency carrier wave, VC. But that carrier wave doesn't travel through a vacuum. The physical transmission path is an active electromagnetic environment, constantly bombarded by transient electrical interference. A lightning strike or a firing spark plug acts as a broadband transmitter, injecting rapid, high-voltage energy spikes directly into the atmosphere. These rogue electrical discharges collide with the carrier wave mid-flight. Because they share the same physical medium, the interference merges with the transmitted signal long before it reaches the receiving antenna. Mathematically, this external noise adds directly to the voltage amplitude of the carrier wave. A pristine sine wave becomes overlaid with sharp vertical voltage spikes. What the antenna actually captures is not the smooth, predictable oscillation generated by the transmitter, but a jagged, chaotic waveform carrying the electrical scars of its journey. Once that distorted wave enters the hardware, the receiver's internal architecture determines the outcome. The circuitry will either allow this environmental chaos to destroy the data or mathematically erase it. An amplitude modulation, or AM, receiver operates by tracking the vertical limits of the incoming signal. It extracts information by continuously tracing the linear variations in the wave's peaks, a boundary known as the envelope. When an external noise spike pushes the voltage peak artificially high, the AM envelope detector registers that spike as a valid change in the signal. The detector cannot mathematically distinguish an interference spike from actual encoded data. Because the amplitude itself constitutes the data in an AM system, any attempt to slice off those noise spikes physically removes the encoded audio. You cannot clean the wave without destroying the information. Frequency modulation solves this by abandoning the amplitude domain entirely. In an FM system, the carrier amplitude is locked to a strictly constant value. The FM receiver encodes information solely through the instantaneous frequency deviation, FD. The data is represented by how rapidly the wave oscillates, allowing the system to completely ignore the vertical height of the waveform. Instead of tracking peaks, the FM receiver looks at the horizontal axis. The critical data points are the zero crossings, the exact moments the waveform intersects the baseline. By making vertical voltage changes irrelevant to the data structure, a communication system achieves immunity to the most common forms of atmospheric and electrical noise. To weaponize this constant amplitude property, the FM receiver relies on its first major architectural block, the limiter circuit. The limiter operates by enforcing strict boundaries. It deliberately restricts the maximum allowed amplitude of the incoming signal to hard positive and negative voltage limits. Any voltage that exceeds these predefined horizontal thresholds is aggressively sheared off. In an AM system, this severe clipping would render the audio unintelligible. But in an FM system, the vertical height of the wave carries no value, so decapitating the waveform leaves the baseband information unharmed. The true information remains locked in the timing of the zero crossings. Even with the tops of the waves sliced flat, the horizontal spacing between these intersections remains perfectly intact. By intentionally sacrificing the amplitude domain, the FM receiver mathematically eradicates the primary physical manifestation of electrical noise. The limiter circuit solves vertical interference, but it exposes a secondary vulnerability. Electrical noise does not just add vertical amplitude, it also alters the timing or phase of the wave. We can model this through vector addition. The incoming carrier phasor, S, and the noise phasor, N, combine to create a new composite phasor, C, which is shifted from the original carrier by an angle phi. This geometric error reaches its absolute maximum when the noise vector sits precisely orthogonal to the carrier. We calculate this maximum phase shift as the inverse sine of the noise amplitude divided by the composite signal amplitude. In an angle-modulated system like FM, a shift in phase produces a simultaneous shift in frequency. This phase error translates directly into an unwanted frequency deviation, calculated as the phase shift multiplied by the modulating frequency. Because the modulating frequency acts as a multiplier in that equation, the resulting frequency deviation scales linearly. A constant amount of phase noise produces an increasingly severe frequency error as the audio pitch rises. The math dictates a harsh reality for FM. high-frequency noise components inherently cause the most severe interference, threatening to drown out the higher registers of the audio signal. To protect those upper frequencies, FM architecture employs a two-part system-level countermeasure known as preemphasis and deemphasis. Before the signal even leaves the transmitter, a preemphasis circuit artificially boosts the amplitude of the high-frequency audio components, giving them enough power to punch through the environmental phase noise. Once the signal reaches the receiver and passes the demodulator, it encounters the deemphasis circuit. This is a passive RC low-pass filter, specifically calibrated with a 75 microsecond time constant. This chart shows the opposing curves. The receiver's deemphasis filter begins attenuating signals heavily above a specific hinge point, 2123 Hz, rolling off the upper frequencies at a steep rate of 6 decibels per octave to perfectly mirror the transmitter's boost. That exact hinge point is derived from the filter equation. Cutoff frequency equals 1 over 2 pi times the resistance-capacitance product. This creates a synchronized dual effect. The receiver reduces the artificially boosted high frequencies back to their natural, flat audio response, and in the exact same motion, it crushes the high-frequency phase noise that accumulated during transmission. By mathematically filtering the output, the RC circuit successfully isolates the final audio fidelity from the highest energy environmental interference. These mechanisms provide exceptional clarity, but they extract a physical cost. FM's noise immunity requires a significantly wider consumption of the radio spectrum. While an AM signal produces just 2 narrow sidebands, frequency modulation generates a vast, theoretically infinite array of significant sidebands, distributed according to complex mathematical series, known as Bessel functions. This demonstrates the stark contrast in scale. We estimate necessary channel width using Carson's rule, calculating total bandwidth as 2 times the sum of the maximum frequency deviation and modulating frequency. This demands an allocation of 200 kHz per FM channel. That wide bandwidth enables a unique physical phenomenon called the capture effect. When 2 FM signals broadcast on the exact same frequency, the receiver will lock entirely onto the stronger signal and systematically suppress the weaker one. Because AM detectors continuously read all amplitude variations, they cannot replicate this effect. If 2 AM signals collide, the receiver processes both simultaneously, resulting in a garbled overlap of background bleed-through. The massive 200 kHz footprint is not wasted space. It is the necessary currency spent to purchase absolute noise immunity and total signal isolation. Implementing these concepts originally required immense hardware footprint. Compared to a simple AM detector, early tabletop FM units relied on highly complex, discrete component layouts. Executing precise limiters, phase correction, and wideband filtering demanded massive physical arrays of hand-soldered capacitors, coils, and resistors. The modern solution condenses that entire room of theory into digital signal processing, executed inside microscopic integrated circuits. The physical limiter circuits and passive RC deemphasis filters have been replaced by algorithms. Those precise mathematical operations now execute instantly within monolithic blocks of silicon. The amplitude domain will always remain vulnerable to the chaos of the physical world, but by encoding data in frequency and executing the cleanup through integrated silicon, FM's mathematical immunity became the global standard for high-fidelity communication.